Last time we looked at the slope formula. We said that slope is a number which we can assign to a straight line, which gives an indication of the steepness of that line. Lines with greater slopes, not greater slopes, bigger slopes I should say, whether positive or negative, are steeper, and lines with slopes close to zero are close to horizontal. And if the slope is exactly zero, then it is going to be a horizontal line. And what kind of line does not have a slope? Vertical lines. Straight up and down lines. Slope we say is undefined because defining the slope would involve dividing by zero. We can't divide by zero. So we talked about the slope and calculated the slopes of various different lines. In this case, whoops, case went away. In this case, a particular slope is specified. There's a line that we have in mind that has a slope of 3/4. Now, there are a lot of different lines that have a slope of 3/4. Basically, if we're going with the ratio of 3 up and 4 to the right, to go in the slope, something like that, I guess. A lot of different lines could be about that steep. But if we specify a particular point on the line, well, that locks us into a unique line because we're kind of stuck at that point, can't slide the thing up or down. So we want to sketch the graph. If we know a point and a slope that determines a line uniquely, that's enough information to sketch a graph, and in just a little bit it's going to be enough information for us to define an equation of this line. So begin with the point 2, 1, and really if I could find one more point on this line, that would be enough. We could take a straight edge and connect the dots, and that would give us the graph. How can I find another point on this line? Up 3 and over 4 to the right. So that'll do it. If we think of 3 over 4, or 3/4 as being written as 3 over 4, the positive 3 would have us go 3 up, and the positive 4 would have us go 4 to the right. So if I go 3 up and 4 to the right, that will take us to another point on this line. What point is that? 6, 4. Go from a y-coordinate of 1 to a y-coordinate of 4, 3 up. And we could do this again. We could go 3 more up and 4 more to the right, and that takes us to what point? Looks like 10, 7. Now, if moving up and to the right would take us off of whatever page or graph that we're working on, it might be advantageous to go the other direction. If we take 3 over 4 and write it with a negative numerator and a negative denominator, instead of going up and to the right, then we could move the point down and to the left. Negative 3 would be negative rise, or 3 units down, and negative 4 would be negative run. The negative horizontal direction is to the left, so 4 units to the left. Of course, we already have plenty of points, but just in case we needed to go the other direction, want to give an indication of how to do so. 3 down, 4 to the left, looks like negative 2, negative 2. Could keep doing that if we wanted to. 3 down, 4 to the left, and what's that point? Negative 6 maybe? Negative 5? Okay, so plenty of points on this line. Let's connect the dots, and this will be the graph. Here goes. Up, and of course it continues down and to the left. So there's a straight line. The point here is that if we know a point on the line and we know the slope of that line, that's enough information to tell us everything that needs to be known about that line. We could take that and sketch a graph. We could take that, and we will in a little bit, write an equation. Okay, more lines to graph. I'm going to zoom out of this just a little bit so I can capture all this at once. I'm going to zoom out one more time. I just don't like it the way it does the equal sign there. So it might be the print might be a little small, but I could enlarge it somewhat after I capture this. Just so it still says, there we go. Graph the line that passes through the point 3, negative 2. 3, negative 2 is right there. It has a slope of 0. Again, What kinds of lines have 0 for their slope? Straight across lines, horizontal lines. So let's draw one of those. Going through that point and going straight across, we have a horizontal line. So there's the point, 3, -2. The y-intercept here certainly is going to be -2, so we'll call that 0, -2. Other points on the line, -6, -2, 8, -2. Let's see what else. 5, -2. And we can plot as many of these as we want to. Not only do we want the graph's easy enough, it also wants an equation for the line. So we want to write an equation so that every point on the line has to satisfy the equation. Well, the only thing that really has to be satisfied in order to qualify to be a point on this line is what? What do all these points have in common? Y equals -2. So if we write that down as our equation, y equals -2, that describes every point on this line and only the points on this line. Go above it, y is greater than -2. Go below it, y is less than -2. If y equals -2, it's a point on this line, and every point on this line has -2 for its y coordinate. So this is a really good equation for the line. In general, if we're in the business of finding equations of straight lines and we happen to cross a horizontal line, quick and easy way to write an equation for a horizontal line is to find the y coordinate of any point on the line. You could use the y-intercept or any point at all. Y equals that number will give you an equation of that line. So, nice way to write equations of horizontal lines. Vertical lines are not much more difficult. Example 4 gives us the same point. Says sketch the graph of the line, but in this case it's the line that does not have a slope. Graph the line that passes through the point 3, -2 and whose slope is undefined. Well, the kind of line that doesn't have a slope is the vertical line. So it's not much trouble to draw a vertical line going through this point. Here goes. Writing an equation, it's good to note some other points on the line. The x-intercept is 3, 0. Other points, not necessarily key points, but just points, 3, 4, 3, 7, 3, -8, and we could list a bunch more if we wanted to. What do all these points have in common? X equals 3. So in order to be a point on this line, your x-coordinate must be 3. And that's all it takes to be on this line. If you have an x-coordinate of 3, you're going to be on this line. So this is an equation. In general, if you want to find an equation of a vertical line, if we're in the process of collecting information about a line with a view toward writing an equation, if it says the slope is undefined, or if it says it's vertical, then you write x equals blank, and you can fill in the blank if you can find the x-coordinate of any point on the line. So x equals a number is a good way to write the equation of a vertical line, just like that. Non-vertical lines, non-horizontal lines, the equation will be a little bit more challenging. If we're thinking about equations of lines, probably the most popular way to write an equation of a straight line is this one. Slope-intercept form. Slope-intercept form is given right here, y equals mx plus b. We recognize this as the equation of a straight line because it has nothing but x terms. There's the x term there. Y terms, there's a y term there, and a constant term. If there's an x squared, it's not going to be a straight line. If there's a y squared, it's not going to be a straight line. If there's a square root of some expression with x's and y's in it, probably not going to be a straight line. But if there's just x terms, y terms, and constant terms, we can expect that the graph will be a straight line, so we can call this a linear equation. Now, slope-intercept form is kind of special. It's useful in a couple of ways. we haven't technically talked about functions in this class, haven't defined functions or started talking about domain and range, any of that. But a little bit of foreshadowing here. I know that you've seen functions in previous algebra classes and know kind of what f of x means. If we have an equation of a line in slope-intercept form, y equals mx plus b, it makes it really easy to write it as a linear function. All we have to do is pick up the y and think of a good name for a function, f, g, h, something like that. Replace the y with the f of x function notation, and then we've got ourselves a linear function, f of x equals mx plus b. So that's one good example of usefulness of slope-intercept form. Maybe even a better one, I think, is if someone hands us the equation of a line, it's a quick and easy way of finding the slope. If we need some information about a line, the slope is a real principal piece of information that we need. So if we can take the equation, solve it for y, and just look at it, there it is, the slope. Without that, we have to use the slope formula, which means we've got to find 2 points on the line, and sometimes that takes some work. So that's the first way we'll see of using the slope-intercept form. I don't know if I caught that 10 or not on the end. Let's try that again. So example 5 is fairly short and sweet. We have 2 equations. They're equations of straight lines, and we just want to find the slope of each line. Part A, we compare it to y equals mx plus b. It compares very favorably to y equals mx plus b. It looks like it's in slope-intercept form. So what's the slope? 6. M equals 6, just like that. M equals 6. Without that, we would have to find 2 ordered pairs that satisfy this equation and then apply the slope formula. Not difficult, but it takes longer. The B part appears not to be in slope-intercept form, just one step away from slope-intercept form. What can we do? Divide both sides by 3. We have 3y on the left. What we want is 1y on the left, so 3y divided by 3 equals 12x plus 10 divided by 3. Y equals 12x divided by 3 plus 10 divided by 3. So y equals 4x plus 10 thirds. What's the slope? 4. There we go. So not difficult, but just a way to use the point slope form to find the slope of a line. I think is easier, shorter, sweeter than finding 2 points that satisfy the equation and then using the slope formula. Okay, we want to graph a line that has a particular slope and goes to a particular point. This really doesn't have a lot to add to that line that we graphed a little bit ago that went through the point 2,1 and had the slope of 3/4. I think the point of this example is that if someone gives us the slope-intercept form, or maybe we find it on our own, the slope-intercept form of the equation of a line, we can get from here to a graph pretty quickly. Because if we know the y-intercept, what's the y-intercept? I guess I really didn't emphasize that in our previous discussion of the slope-intercept. I've emphasized the slope. The intercept part is that the number 3 represents the y-coordinate of the y-intercept. So immediately we can plot the point 0, 3. And then if we know the slope, 1/2, we can do we can do the rise over run thing, 1/2, 1 up, 2 to the right, and plot additional points like that. 1 up, to the right, 1 up, to the right. Get tired of that? 1 down, 2 to the left, 1 down, 2 to the left, and maybe down to the x-axis there. Not difficult to graph the line, but the point here is that if we have the slope-intercept form of the equation of the line, because we can get a starting point from the y-intercept and the slope from the m right there in front of the x, we can graph this line. So it's kind of a handy way to get enough information quickly from an equation to sketch the graph of a line. It's not the only way. get enough information. If the line is maybe in a different form, it might be better to find an x-intercept and a y-intercept and plot those points on the x and y axes and connect the dots. Maybe that's a more efficient way depending on the form of the equation. Yes, Sailor.
Isn't that one up 1 over 1? Or isn't it supposed to be up 1 over 2?
Up.
Doesn't that put it on a different line?
It is up 1 over 2. Up 1 over 2.
But the lines up there look like it's up 1 over 1. Like the slope is 1, 1.
It could be because of the aspect ratio. When we do one in a few minutes, what I'm going to do is stretch the graph horizontally a little bit. On my screen, it looks like it's up 1 and over 2. As I look at the screen up here, it looks like it's the little squares on the grid are actually rectangles that are taller than they are wide.
Yeah.
So when we do the next example where we graph something, I'm actually going to stretch it. It's going to be really important when I draw two lines that are supposed to be perpendicular to each other. They'll look perpendicular to me, but they won't to you up on the screen if I'm not careful to do that. So I'm going to stretch it out so they actually look like squares instead of little vertical rectangles. So I think I have the points okay, but I understand why it might not look like that. Point slope form. To this point, we've been given equations or information about a line, and we have sketched graphs. If we're given information about a line, that is enough information, say a point and a slope, is enough information to sketch the graph, it also ought to be enough information to write an equation with x's and y's in it so that every point on the line represents an ordered pair that would satisfy the equation. To kind of see where this point slope form comes from, consider a straight line. We can do this with lines with positive slope. We can do this with lines with negative slope. Even a horizontal line with a slope of 0, we can use the point slope form. Just want to know that the point slope form cannot be used to write an equation of a vertical line, because to do so you need a point and a slope, and vertical lines do not have a slope. So for non-vertical lines, this is going to be a very effective way of finding an equation of a line. So imagine that we know or can figure out a point on the line that we're looking for. X sub 1, Y sub 1 is a point on the line. Imagine those are numbers there. What we want to do is write an equation so that if x, y is any other point on the line, and the slope of the line is m, that xy will have to satisfy the equation. Now what we can do is use the slope idea. That's really half of what we know about it. We know a point and we know the slope. So we can calculate the rise. The rise is going to be the second y minus the first y. So we go from a point with a y coordinate of y sub 1 up to a point with a y coordinate of y. So y minus y sub 1 is the rise. The run is x minus x sub 1. It's the second x minus the first x. So if we take this ratio, y minus y sub 1, and divide it by x minus x sub 1, what does that have to equal? Rise over run is the slope. So if we're given that the slope is m, that has to equal m if that point is on the line. Now this would work for an equation of the line going through the point x sub 1, y sub 1, and having a slope of m. But an equation without fractions beats an equation with fractions any day. So to get rid of the fractions, we multiply both sides by x minus x sub 1. When we do that, we get y minus y sub 1 equals m times x minus x sub 1. And this is the point slope form. This should definitely be on your list along with the slope formula, along with slope-intercept forms, important forms and formulas to memorize, be able to use on a test to find equations of lines and information about straight lines. So if someone gives us information about a non-vertical line, First thing to do is write down the point-slope form, look for a point and a slope, and then substitute. Next example gives us the information exactly like we would like it. Subsequent examples will give us enough information, but maybe not exactly like we would like it. Find an equation of the line immediately. I see that the line has a slope, and I write down the point-slope form. And then I go back to reading the example. Find an equation for the line that has a slope of 3/4. Okay, so m equals 3/4. And goes through the point 2, 1. That means that x sub 1, and this point that's given, is 2. And y sub 1 is 1. So we know the x coordinate and the y coordinate. I don't know if I had to do that. Just an arrow will suffice. But the x sub 1, y sub 1, the one with the subscripts, I should say, the point with the subscripts, that's where we substitute the coordinates of this point that's given. The x and the y are just going to stay x and y. We never want to substitute any numbers for those in the point-slope form because we want an equation with an x and a y in it as our final answer. So the x and y just stay x and y. We'll substitute. Now when we substitute for the y sub 1 and for the x sub 1, it's not a bad idea to enclose the y sub 1 and x sub 1 in parentheses, particularly if we're substituting negative numbers for x sub 1 and y sub 1 so that the minuses don't bump into each other. It's important. If we're substituting positive numbers, although it doesn't hurt, it's not that big a deal. I'm even going to enclose the 3/4 in parentheses because I'm technically substituting 3/4 for m, but not a huge deal. As I begin to simplify that, most of the parentheses just melt away, and we're left with y minus 1 equals 3/4 times x minus whatever 3/4 times 2 over 1 is. We have an equation. We could leave it like this if it didn't say put it in slope-intercept form. Since it says put it in slope-intercept form, got to do a couple more steps, get y all by itself on the left, and simplify the right-hand side. So, what's 3/4 times 2? 3/2. 3/2. The 2, you could divide 2 by 2 and get 1. You could divide 4 by 2 and get 2, and sure enough, that's 3/2. So we write minus 3/2. If you wanted to write minus 1.5, you could probably get by with that since it's a terminating decimal. But I want you to be comfortable dealing with the fractions if necessary. So I'm going to leave it minus 3/2. Almost there, add 1 to both sides. And y equals 3/4 x. Cancel those 1s. Negative 3/2 plus 1 gives us what? Minus 1/2. Is that clear in your thinking? Negative 3/2. I guess plus 2/2 would be one way to think about that. That would give you negative 1/2. So we write this, y equals 3/4 x minus 1/2. Now, invoke your short-term memory here. This particular equation is one that we sketched the graph of maybe 10, 15 minutes ago. Remember that one? It might have been here. Nope, maybe it was there. There it is. This is the graph of the straight line that goes through the point 0.21. It has a slope of 3/4. So I'm going to capture this and compare to what we have over there. Shrink it down just a bit. Does this seem to be consistent with what we have for our equation? I guess in particular, the key thing that jumps out that we'd want to check is the y-intercept. According to our equation, y equals 3/4 x minus 1/2, what should the y-intercept be? Yeah. Maybe if I do a little bit better job of connecting those dots, then it'll look a little bit more like it goes through that point. 0, negative 1/2. On my original graph, I didn't miss it by much, but maybe just a little bit. 0, negative 1/2. What we're also saying is that every point on this graph is an ordered pair that satisfies this equation. So we should check 2 or 3 of them. Let's check 2, 1 for sure because that point was given. If x equals 2, and we multiply 3/4 by 2 and subtract 1/2, do we really get 1 for y? We need to, otherwise something has gone terribly wrong. So let's hope it works. Do we get 1? 3/4 times 2, we still feel good about calling that 3/2, right? 3/4 times 2 equals 3/2. 6/4 is equal to 3/2. 3/2 minus 1/2 equals how many halves? 2 halves? Does 1 equal 2 halves? Let's say yes. Let's check one more. Anybody have a preference, 6/4 or 10/7? Which one should we check? All right, 6/4 it is. 4, is that what we get when we take 3/4 of 6 and subtract 1/2? 3/4 of 6, 18/4. 18/4 reduces to what? 9/2. And if we take 9/2 and subtract 1/2, how many halves do we get? 8/2. Can we say that's equal to 4? Yeah, that's equal to 4. So it works for 6/4. It'll also work for 10/7. It'll work for -2/2. It'll work for -6, -2, -2. It'll work for -6, -5. Every point on this line, plus a lot more that we didn't label on this line, represent ordered pairs which will satisfy this equation. This graph is the set of all points that satisfy this equation. So we call this the equation of the line, and this is the graph of the line. Example 8 gives us enough information, but not exactly the information that we might like to have. Find the equation of the line that goes through the points 2068 and 100-212. To find an equation of a straight line using the point-slope form, we need a point and a slope. What it gives us is 2 points, but it does not give us the slope. So what do we do?
Is it like y2 minus y1 over x2 minus x1?
Yes. y2 minus y1 over x2 minus x1. We use the slope formula and we find the slope. So m equals 212 minus 68. That is, assuming I call this one x sub 1, y sub 1, and call this one x sub 2, y sub 2. The difference in the y's, we're going from 68 to 212, so 212 minus 68, over the difference in the x's, 100 minus 20. And I don't know, maybe calculator time. We get a fraction that reduces a whole lot. What's the reduced version of this? 9/5. If we divide both the 144 and the 80 by 16, 144 divided by 16 equals 9, 80 divided by 16 equals 5, or you can divide them both by 2, and both by 2 again, and both by 2 again, and both by 2 a fourth time, and eventually get 9/5. So that's the slope. Now we have more information than we need. All we need is a point and a slope. We have 2 points and a slope. So this means, since both points were used to find the slope, either point will work. Which one do you like better? 2068 or 100-212? 2068. 2068. I mean, conveniently, it's already labeled x sub 1, y sub 1. I remarked yesterday to my 8 o'clock class, 9 out of 9 college algebra classes prefer the point 2068 whenever I put it up for a vote. It always happens like that, and this semester has been no exception to that rule. 3 out of 3 it's been. Y minus 68 equals 9/5 times x minus 20. this is an equation of the line that goes through these 2 points. But the problem says put the final answer in slope-intercept form, so we keep working on it. Simplify the right-hand side. Isolate the y on the left-hand side. Y minus 68 equals 9/5 times x minus 9/5 times 20 over 1. What is 9/5 times 20 over 1? 36 is what I'm hearing. 5 goes into 24 times, and 4 times 9 is 36. So 9/5 x minus 36. Need to isolate the y, so add 68 to both sides. When we do, we get y equals 9/5 x, looks like plus 32, plus 32. So there we go. We could check this. We could substitute 20 for x and confirm that that gives us 68. We could substitute 100 for x. That's probably not too tough. 9/5 of 100. 5 goes into 100 20 times. 20 times 9 is probably something like 180. What's 180 plus 32? It sound like 212? Okay. So I feel pretty good about this. This would be, and is, the final answer. But it's a special final answer. Let's see if we can say some things, some of which may be interesting, about this final answer. This particular linear equation has some significance as far as the real world is concerned, unlike a lot of things we do in this class. What's the significance of this equation as far as the real world is concerned? Temperature. Yes, temperature. What's the significance of the point 100, 212? Boiling point. 100 degrees Celsius, 200 degrees Fahrenheit, what we typically think of as boiling point of water under, I guess, close to sea level or at sea level. 2068, the significance of that may be kind of lost on us because I think it's a little bit subjective. But today in this room, does it feel like it's about 20 degrees in here? Is that about right? 20 degrees? Or does it feel a little warmer than that, a little cooler than that? A little warmer, perhaps? 20 degrees Celsius, 68 degrees Fahrenheit is commonly thought of as being comfortable room temperature. Might want to have sleeves at that temperature, I don't know. Most of us do have sleeves today. But that's thought of as room temperature. Other points. What's the y-intercept? What's the significance of the y-intercept here? Freezing point, 0 degrees Celsius, 32 degrees Fahrenheit. Let's see what else. We're going to the realm of trivia here, but I think it's interesting trivia. 37 degrees Celsius. How many degrees Fahrenheit? Who knows this?
90-something.
It's 90-something, yes. It is 90-something. You can punch it up on a calculator. 9/5 times 37 plus 32. But someone have a more precise guess than 90-something? Oh, it's a good guess because it's an accurate guess. 9/5 times 37. 98.6. That's a familiar number. 98.6, what is sometimes thought of as normal human body temperature. And then one more. 40 below. -40, -40, yeah. The point where it's the same numerical value on both scales. 40 Celsius degrees below 0 degrees Celsius is the same actual temperature as 40 Fahrenheit degrees below 0 degrees Fahrenheit. So if it's kind of cold outside, not in northwest Florida, but parts north of here, 40 below is enough to express the temperature without specifying Celsius or Fahrenheit. All right. Thank you for putting up with that. I just think that's interesting. Nice linear relationship that exists between the Celsius scale and the Fahrenheit scale. Parallel lines. I want to talk about the relationship between slopes of parallel lines. First, I will attempt to draw a couple of parallel lines. Sometimes it goes well. That was a pretty good attempt. Let me try one more time. Slightly better, maybe. Definition of parallel lines. Two lines in the plane that do not intersect at all. That's what we mean by parallel lines. Does it look like these lines could pass as parallel lines? Maybe. Maybe. If so, which line is steeper? If so, I'd like to say they have the same amount of steepness. If the bottom one is steeper, and maybe you're just being nice and really thinking the bottom one's steeper, you just don't want to say it. If the bottom one were truly steeper, then at some point it's going to catch up to the top line. And they would intersect and they would not be parallel. If somehow the top line were steeper, down here to the left somewhere, they would intersect and they would not be parallel. They really kind of need to be the same amount of steepness in order to be parallel. So is it reasonable, since slope is an indication of the steepness of a straight line, that we say that a couple of distinct non-vertical lines are parallel if and only if they have the same slope? Is it going to be okay to say that? Why do we have to say non-vertical? It's certainly possible for vertical lines to be parallel. In fact, if we have two vertical lines, they will be parallel to each other. It'd be nice to be able to say they have the same slope. Why can we not say that? Why can we not say that two vertical lines have the same slope? They don't have a slope. They don't have a slope. We can say the same thing about their slopes, namely, they don't have one. But we can't say they have the same slope. These two, if the slope of this line, just kind of staring that line down, what would you say is the slope of that line? What do you think? Some fraction? Single digit numerator, single digit denominator? What would you say? What's the slope of that line? How far up, how far over do we go? What's the slope? I don't know. It's different on my screen than it is up there, so I hesitate to guess. Would you say maybe 1/2? Is that believable on the screen that you're looking at? But we could go with like 2/5 if you'd rather. Sure? 2/5. Okay. If that one has a slope of 2/5, then this one down here would have what slope? 2/5. Yeah, just like that. So, distinct non-vertical lines are parallel if and only if they have the same slope. What about if they're perpendicular to each other? According to this, non-vertical, non-horizontal lines are going to be perpendicular to each other if, when you multiply their slopes together, you get -1. Now, I want to drag this out so that the height of each little square is the same as the width of each little square, as it's supposed to be for squares. So, is that enough? Or should I go a little bit farther? How about that? Do they look like squares? Or are they too wide now? Do they look like squares? Okay, I'm going to say they look like squares. If we wanted to consider a couple of perpendicular lines, suppose one of them had a slope of 2/3. I'm just going to make up a line here and graph it here, something that has a slope of 2/3. What can I multiply 2/3 by and get -1 as the answer? -3/2. So it has to have the opposite sign if I'm going to give it a product of -1, and the absolute value of that number I'm multiplying by needs to be the reciprocal of the original. So 2/3 times -3/2 equals -6/6, which reduces to -1. So just pick a point anywhere. I'm going to start here. And for the one with a slope of 2/3, I guess I need to go 2 up, 3 to the right. So here it goes. 2 up, 3 to the right. 2 up, 3 to the right. 2 up, 3 to the right. Or if I want more points down here to the left, 2 down, 3 to the left, 2 down, 3 to the left. Connect the dots, and this will be a line that has a slope of 2/3. There we go. M equals 2/3. When I try to sketch the graph of the line of a line, it's going to make one up that has a slope of -3/2 and see if it looks like it intersects this line at a right angle. So here goes. Pick a point somewhere. Oh, where's a good point? Maybe here. Let's start right there. If I want to go from here and intersect this line, I probably need to go up. If I take -3/2 and want it to have positive rise, it better have negative run. So if the 3 means go 3 up, what does the -2 mean? To the left. To the left. So 3 up and 2 to the left. 3 up and 2 to the left. 3 up and 2 to the left. Does not look perpendicular at all on my screen, but maybe up there. Maybe. It looks like it could be perpendicular if I connect these dots. Here goes. It's close. I think I stretched it too much. I think I stretched it too much horizontally so that the squares are a little too wide. Nonetheless, I'm going with it. I'm going to redo it. Now, what I have to do here is draw a parallelogram like so. This needs to be parallel to the blue line. This needs to be parallel to the red line. So it gives the appearance that these are intersecting at a right angle. So there we go. There's the relationship between non-vertical, non-horizontal lines that are perpendicular to each other. Now, why do I have to say non-vertical, non-horizontal? What if I have a vertical line and a horizontal line? Are they going to be perpendicular to each other? Vertical line, horizontal line? Yes, they're perpendicular. They intersect at a right angle. But to compare their slopes, the vertical line doesn't have a slope, and the horizontal line has a slope of 0. Well, we have to calculate the opposite reciprocal, and 0 does not have a reciprocal, so we have to leave out that case. Exercise, example 9 here. Suppose someone hands us a straight line, and it has a particular slope. Let's say this line someone gives us has a slope of 2/5. Any line that's parallel to that line with a slope of 2/5 would have what slope?
2/5.
2/5. Same slope. So 2/5. Okay, so we got a line with a slope of 2/5, maybe another line with a slope of 2/5. Any line that's perpendicular to either one of those lines would have what slope? Opposite sign. Reciprocal? -5/2. So we multiply 2/5 by -5/2, we get -1. So perpendicular line. Suppose on the other hand, somebody gives us a line and it has a slope of -4. Kind of steep. What? 1 to the right, 4 down. 1 to the right, 4 down. Any line that's parallel to that would have what slope?
-4.
-4. What's the slope of a perpendicular line?
1/4.
1/4. Change the sign, make it positive, take the reciprocal, get 1/4. So that's not going to be very steep. It'll be 4 to the right and just 1 up. So something like that. A given line has a slope of 0. It's horizontal. So any line that's parallel to that would be horizontal and have what slope? 0. On the other hand, if we have a horizontal line and we're wanting the slope of a perpendicular line, something perpendicular to horizontal would be vertical, and
None, no.
and not have a slope, no slope at all, undefined slope. There we go. Slope of a vertical line is undefined. We start with a vertical line. We said a moment ago, what do we say? These two lines are parallel, even though neither one of them has a slope. So if we have a line that doesn't have a slope, parallel line is also going to be vertical and also not going to have a slope. But what if we go back here and consider a line that's perpendicular to a vertical line?
Zero.
Its slope is 0. There we go. All right, hopefully that does not look like a weird 6 or something. That's a 0. All right. So hopefully not a difficult exercise, but an exercise that we sometimes have to carry out in order to make sure we're working with the correct slope. Example 10, A and B involve the same type of process. Basically, it amounts to figuring out the slope in order to do this. So I'm going to stretch this a little bit, but I'm going to omit the A part and just do the B part, which actually involves an extra step. So example 10, we're given an equation of a line, and we want to see if we can find an equation of a line that's perpendicular to that and that goes through a particular point. Are they squares yet? I think maybe so. In fact, this one right here looks like it's almost too wide. So I'm going to go with this picture. Example 10. Find an equation of the line that's perpendicular to the line whose equation is 2x minus 5y equals 8. Now, we don't technically need a picture. If you know exactly what's going on here, then you don't need a picture of this. But I think it's helpful to have a picture because it's a very visual type problem. We've got a line that's given, 2x minus 5y equals 0. The x-intercept of this line is 4. Check it. Does the point 4, 0 satisfy this equation? 2 times 4 is 8. 5 times 0 is 0. 8 minus 0 equals 8. Feel good about the point 4, 0? What's the y-intercept of this line? I don't know. One way to substitute 0 and solve for x might be a good idea to take the equation and actually put it in slope-intercept form. So let's do that and see if we can find the y-intercept that way. 2x minus 5y equals 8. If we subtract 2x from both sides, we get negative 5y minus 2x. Oops, sorry. Negative 5y equals negative 2x plus 8. We need one y on the left, not negative 5y, so divide both sides by negative 5. Negative 2x plus 8 divided by negative 5. Good grief. So sorry. That's a y there. So y equals negative 2x over negative 5 plus 8 over negative 5. And negative 2 over negative 5 doesn't really reduce, but a negative divided by negative is a positive. So y equals 2/5 x minus 8/5. Now with that, is it easier to see what's the y-intercept? Negative 8/5. Negative 1 3/5 or negative 1.6. So we can put it right about there. If we put the y-intercept right there and connect the dots with a line that looks like this, that's the line that's handed to us. That's the line whose equation is 2x minus 5y equals 8. Now, what do we want to find? We want to find the equation of the line that goes through the point 6,5 and is perpendicular to this line. That's what we want. Now, to write an equation of the line, we'll use the point slope form. Y minus y sub 1 equals m times x minus x sub 1. In order to use the point slope form, we need two things. We need a point, which we have, and a slope, which we sort of almost have. That's x sub 1. That's y sub 1. I think we know the slope of the blue line. What's the slope of the blue line? 2/5. So what's the slope of any red line that's perpendicular to this? Negative 5/2. Opposite reciprocal. So negative 5/2 m perp. equals negative 5 halves, slope of the perpendicular line there. And we can actually graph the line if we go 5 down and 2 to the right, and 5 down and 2 to the right, or if you want, 5 up and 2 to the left. Let's see if it looks perpendicular, and then we'll find the equation. I hope it looks perpendicular. Ooh, just looked like a straight line. Maybe I would settle for that.
Where did you get the 4 0 from?
So rough. The 4 0?
On the blue line.
Oh, that's a good question. I just kind of waved my hands at it, and it appeared. Officially, when we're searching for x-intercepts, the official procedure for looking for x-intercepts, and I'll go back to blue here for this, x-intercept, I just don't have room, right here. X-intercept, we let y equals 0, because every point on the x-axis has a y-coordinate of 0, and we solve for x. So basically I said 2x minus 5 times 0 equals 8. So 2x minus 0 equals 8. So if 2x equals 8, then we know that x equals 4. So if y equals 0 and x equals 4, that's the point 4, 0. So I kind of did that by using the cover-up method. I covered up the y term because 0 basically kills that term, and we can cover it up. And then you get 2x equals 8, and you can solve it that way. So get the x-intercept pretty quickly. I could have done the same thing for the y-intercept, but the y-intercept involves a fraction, the negative 8/5, and I didn't want to go there with that method, so I just put it in slope-intercept form. I think we're there. We agreed on the point was given. We agreed on the slope. So let's find the equation. Y minus 5 equals negative 5 halves times x minus 6. There we go. That's the equation, as usual. It asks for it in slope-intercept form. So simplify the right-hand side, isolate the y on the left-hand side, and we'll get there. Y minus 5 equals negative 5 halves x. Now, negative 5 halves times negative 6 is going to be something positive. Negative times negative is a positive, so it will be positive whatever 5 halves times 6 over 1 is. What's 5 halves times 6 over 1? It's 15. It's 30 halves, and that reduces to 15. So, plus 15. Isolate the y on the left-hand side. Add 5. And we get y equals negative 5 halves x plus 20. And I think if we were to extend this up here, only so far to let me extend it, the y-intercept of 20 would be evident right up there somewhere. So y equals negative 5 halves x plus 20 is in red there, the final answer that we're looking for. And you can see what we'd do if we wanted an equation of a parallel line that goes through that point. Instead of using negative 5 halves, we'd just stick with a slope. We'd use 2/5 as a slope and find the equation of the parallel line that way. So 10b is what it is. 11 should be a short, sweet example. We talked about finding equations of vertical lines and horizontal lines. We have the opportunity to do this here, but still the parallel and perpendicular idea. Maybe the picture would help. Find an equation of the line that's parallel to the line x equals 4 and passes through the point 6, 5. So if I say the point 6, 5 is maybe right there, and x equals 4, that's the y-axis and that's the x-axis, x equals 4 might be this. I guess before I draw the picture, I should ask, x equals 4. That's one of those special ones. Is that horizontal line or vertical line? Of course, I've spoiled that now. having sketched the graph. But you want to ask yourself that question. Is that x equals 4? If x is always 4, does that go straight across or straight up and down? Well, if you plot a bunch of points that all have x coordinates of 4, 4, 0 for 1, and 4, 1, 4, 2, 4, 3, 4, 4, it's a straight up and down kind of line. It's vertical. So that's what that looks like. Now, if you want a line that's parallel to that, that better be vertical too. So all you have to do is figure out, okay, the x coordinates of all the points on this line are the same, and they're all equal what? Oh, sorry. There we go. In particular, this point right here, what are the coordinates of that point? The x-intercept. Would you believe 6, 0? So we've got 6, 0 and 6, 5 and infinite supply of other points on this line that all have x coordinates equal to what? 6. There we go. So x equals 6. So not difficult. Just have to know, okay, parallel to a vertical line, therefore it must be vertical. And so if you write the equation of the vertical line, x equals a number, then it's x equals whatever the x coordinate is, and the x coordinate is 6. The b part would have us write an equation of the line that's perpendicular to x equals 4. All right, if it's x equals 4, it's vertical. If it's perpendicular to x equals 4, it's what kind of line?
Horizontal.
Horizontal. Straight across it goes, horizontal line. Now, horizontal line, the y coordinate never changes. The y coordinate here is, the point here is 6, 5. This point is 4, 5. This point is 0, 5. So the equation of this line is y equals what? 5. Just like that, y equals 5. Not a difficult problem, but vertical versus horizontal, you don't need to pull out the point slope form for that. Point slope form will work for the horizontal line, but you don't need it, and it won't work for the vertical line. So just some observations. The example 12 I want to skip. Do we have almost 15 minutes? Not quite. I want to give you kind of an idea of how to approach example 13, this linear regression equation. It is a calculator-driven problem. Did you bring your calculator today? If so, you want to get that out. If not, be sure and bring it next time, because we'll probably do one more example of this next time. Uh-oh, spoiler alert. Oh, touch the top of the screen. Got to avoid that. There, I just want to be able to see the, So it's not a matter of touching the top of the screen, it's a matter of getting too close to it. There we go, and this one, scoot that to the left. Okay, so what I want to do is get the calculator to plot these points and to find the equation of the straight line that comes as close as possible to as many of these points as possible. They're not all on the same straight line, but they're pretty close to being on the same straight line. And we want to get the calculator to find the equation of what's called the line of best fit. So basically what's happened is this. Someone with a stopwatch and a thermometer and way too much time on their hands went out and counted cricket chirps. Measured the temperature and the number of chirps that happened at that temperature. When the temperature was 44 degrees, 20 cricket chirps were counted per minute. I don't know if it warmed up or it cooled off, but at some point the temperature was 56 degrees, 65 cricket chirps were counted. When the temperature was 67 degrees, 110 chirps per minute were counted. So it looks like the warmer it is, the more chirping takes place, or maybe the more chirping that takes place, the warmer it is. It looks like there's a correlation between chirping frequency and the temperature. So we would just want to see if it's a linear correlation and see if we can describe that with the equation of a straight line. Calculator will do this for us. In order for that to happen, let's do a few things. First, we eventually hope to graph this, so press y equals to get to this screen. If there are any equations that you have there, clear them. If they're near and dear to your heart, you can simply deselect them and work with them later, or just ignore them. But I want to make sure that's nice and clear so it doesn't get in the way of anything that we want to do here. So y equals should be clear. Now, press the stat button. You see the stat kind of in the middle toward the top, right there, where it says stat. Press that. Now try to press it again. There we go. Takes you to a screen that looks like this. Number 1 on the list on the Edit menu says Edit. Press 1 to go to the Edit menu. Now when you go there, you should see an L1 list and an L2 list at the top. Let's just pause and make sure everybody that's following along sees the L1 list and the L2 list. You see those?
Yeah, but mine doesn't have any numbers.
No numbers. I will put those in there in a moment, but you do have the L1 and the L2 list. Now if they have numbers but they're different from these numbers, what you can do is one of two things. One that takes longer and the other that's more dangerous. The one that takes longer is to delete them one at a time. So if I didn't like this 90, I could press delete. And the 100 I can press delete, and the 110 I could press delete, and they go away. If you don't have many of them, it's sufficiently efficient, I guess, just to press delete multiple times and get them to go away. If you have 100 of them, then that takes a long time. What you would want to do is go up to the top where it's on L1 and don't press delete. Danger, caution, warning. Do not press delete up there, because if you do, what happens, let me go to the L2 list and press delete. L2 goes away, and then panic sets in, particularly if it's late at night and you're trying to get the homework finished up or quiz or whatever, or if it's on a test. If it is on a test and you blow away one of your lists, just let me know and I'll do what I can to help you get that list back. What you can do is notice on the delete up above that is INS for insert. If you press second and then the delete button for insert, then notice on the 1, 2, 3, 4, 5, 6 you have little L1, L2, L3, L4, L5, L6 respectively. So if you press second L2, it will, and then enter, it'll bring back the L2 together with the data that were stored in that list. So if you delete one of your lists, it's okay, it's not the end of the world, you can get it back, but it's just better to use clear. And if I go to L1 and press clear and then down, then it clears the list, it goes away. Nothing happens at first, but then you press the down arrow and then the numbers go away. Take the X values, and as they were before, type those in the L1 list, 20, 40, 45, and so on. Oops. There's that 110. Once you type the 110, press the right arrow, and that'll take you to the L2 list, and then you can type the 7 numbers in the L2 list. You want to make sure that there are no numbers below these lists, that you have the same number of numbers. You don't have an extra one in one column or the other. This will give what's called a dimension mismatch error, where it's trying to plot a point that has an x coordinate but does not have a y coordinate, or vice versa, and that's a frustrating error. So we're good with the points. Next, we want to turn a stat plot on so the calculator will actually be able to plot these points. So if you press the second button and then the button directly above that, y equals, notice that y equals has the word stat plot up above it. So second y equals takes you here. They're all off. I want to select number 1 by pressing 1. And then when it's flashing on, I want to turn this stat plot on. So press enter when it's flashing on the on. And then check what else that you see. There are 6 different types of stat plots that you have to choose from. We want the first one. The default is the scatter diagram. There are some others there that you might use in a statistics class, but the scatter diagram is the one we want. Press down. Make sure the X list is looking at L1, because those are our X coordinates. The Y list is looking at L2. Those are Y coordinates. Those can be changed by pressing second and then the number 1 or 2 to change it to L1 or L2. But if they're L1 and L2, then we're good. The mark, I like the square. The pluses and dots can be used, but we're going to have the calculator draw a straight line, and if we just use dots and it gets close to those dots, it might cover them up and we'll forget where they were. So squares. Second quit, second mode. Press the second button, followed by the button immediately to its right. the mode button. Second quit gets us out of that screen. Now, stat plot is on, so it should plot those points if we're in the correct viewing window. Now, the incorrect viewing window for viewing these points is the standard one. If you want to confirm that along with me, press Zoom 6. Zoom 6. We see no points at all. Why don't we see any points at all? They're all outside the standard viewing window. If you look at the x-coordinates, they would have to be between -10 and 10. Y-coordinates between -10 and 10 in order to see these points, but they go up to 20. Two options at this point. Option number one, we could press Window and manually pick the x max to be a number that's greater than 110 and pick the y max to be a number that's greater than 67. That's one option. Since we have the stat plot turned on, the calculator will do this automatically if we zoom 9. Zoom, and 9 is right there. Zoom stat. The calculator goes to the stat plot, and it automatically will set the x-min and the x-max so that all the points on that particular stat plot will fit on the screen. Do you see this picture? If you zoomed 9. You see it? Okay, so they're roughly on a straight line, not exactly on a straight line. Here's the big deal. Problem number 9 on the MyMathLab homework associated with this section, the final part of section 2.3, will ask you to get the calculator to come up with the linear regression equation. Basically, it's the equation of the straight line that comes as close as possible to as many of these points as possible. We also call it the line of best fit. How to do that? Here goes. Stat. So we press the stat button again. Now, instead of going to the edit menu, we press the right arrow to go to the calculate menu. You want to have the calculator calculate the slope and the y-intercept of the linear regression equation. Number 4 on the list is the linear regression equation of the form ax plus b. So press 4. And now what you see will depend on which operating system that you have. The newest operating system will look like this. And if you have the TI-83 Plus or the older TI-84 Pluses, it'll just say lin reg ax plus b at the top, kind of expecting you to do something. If that's what it says, press enter and see what happens. If you see this screen instead, press the down arrow a few times, make sure it's looking at the L1 list, the L2 list, and go down to where it says calculate, and then press enter. And we should all get pretty much the same numbers though, except you may or may not get the r squared and the r. If you don't get the r squared and the r, that's fine. R is for the correlation coefficient. Basically, it's a number which indicates how close to being on a straight line all these points are. If they're all over the place, then it would be close to 0. But if they all are kind of lined up on something that looks like a straight line, it's close to 1, as it is in this case. So don't worry, we don't need the r squared and the r in this class. A equals, if we round to 2 decimal places, A equals 0.25. That is the slope. So y equals 0.25x plus, if we round to 2 decimal places here, 39.52 plus 39.52. That's what MyMathLab wants. It wants this expression right here, each one rounded to 2 decimal places when you do that problem number 9 in the homework. Now, to see what that does for you, if you press y equals, you can graph this by typing in 0.25x plus 39.52. Y equals, and just type it in manually. Graph. And it looks like this. It is the straight line that comes as close as possible to as many of these points as possible. Called the linear regression equation. It's the equation of the line of best fit. And the calculator does it for you. There are precise formulas for finding the slope and the y-intercept. You can find those in a statistics book. But that's beyond the scope of this class. We'll just have the calculator to do it for us.